Probability. So, in a comedic paradox, the probability you encounter at school is probably the most unlikely situations you'll find yourself in, from pulling counters out of a bag to rolling biased dice. In this video, we'll take a look at some of the real-life uses of probability and try and get our head around the mathematics at play. First, I want to talk about certainty and impossibility. In casual conversation, you might say that something is absolutely certain without it having true mathematical certainty. And equally, something deemed impossible might in fact have some minuscule chance of being possible. Colloquially, we use these two terms to represent things with extremely high or extremely low likeliness, as well as things that have true certainty or impossibility. Mathematically, what's impossible or certain is much more limited. The sunrise problem is a thought experiment that tackles this problem of certainty or impossibility, considering something we all might hold to be absolutely true. Tomorrow, the sun will rise. This we can be certain of, without a doubt. And we could extend this thinking by confidently saying that the sun will always rise, not just tomorrow, but the day after, next month, and in years to come. Maybe though, we might want to doubt ourselves, just slightly. We've likely come to this conclusion from repeated observations. Ever since we were born, we recognise this happening, either actually or intuitively. We go to bed when it's dark, and then wake up to the sun rising. Whether it's beginning to peek its head as you're making a morning coffee, or it's already streaming through your curtains in the morning, waking you up before your alarm.
Then put your little hand in mine. There ain't no hill or mountain we can't climb.
All of these experiences build on our certainty that tomorrow the sun will rise. Yet this experience is also conditional and might vary from person to person. A 2-day-old baby might not recognise this, having only seen maybe one sunrise. And a child might still doubt whether this will continue to happen, with more limited experience than adults who hold it to be absolutely true. People who live in the Norwegian town of Tromsø experience midnight sun at the peak of summer and near permanent darkness throughout winter, when the sun never makes it past the horizon line. Their latitude of 69 degrees north means that as November comes around, rather than rising, the sun will skirt just out of sight, instead lighting up the sky with up to 6 hours of sunrise or sunset-like colours. And so for those who live there, the statement doesn't hold true. Each individual then holds a different level of plausibility around the idea that the sun will always rise. Of course, mathematicians being mathematicians have drawn up a formula to explain how we cannot be absolutely certain the sun will rise. The formula, introduced in the 18th century by Pierre-Simon Laplace, imagines that the sun will rise tomorrow, given it has risen k times previously, where the k is a dependent variable, dependent on our individual experiences. And in short, this formula suggests that if we have had 10,000 days of this experience, the probability of the sun rising tomorrow is 10,000 plus 1 divided by 10,000 plus 2, so approximately 0.9999002. So highly likely, but not certain. The sunrise problem gives us a glimmering insight into the stickiness around certainty, and how the mathematics of certainty doesn't always line up with our reality. And with the same thinking, we can see how things we might deem impossible can merely be very improbable, whether colonising Mars or the existence of aliens. It's only our casual experience that deems these things impossible, but the mathematics might tell us a different story. And of course, the idea of the sun rising indeed flips the true physics on its head anyway. Probability has more of a sway in our day-to-day lives than you might imagine. So last night the weather predicted that there'd be a 30 to 40% chance it would snow, which means there's a 60% chance it won't snow, and as you can see, it snowed. The day-to-day probability we encounter when checking the weather falls on a sliding scale between 100% certainty and 0% impossibility. Its actions control so much of our lives, from what to where and how we travel, that we might not recognise how much we rely on probability on a daily basis. To predict the weather, you need to know what's happening right now and what's happened before. A global network of recording devices collect data such as temperature, wind speed, and air pressure. Combine this with satellite pictures and data stretching back to the 1880s when record keeping began, and computers can create models of this data to predict probable scenarios in order of likeliness. So along this line we can place all possible outcomes as a given probability. For instance, a 50% chance of rain, as seen here, tells us that it's equally likely to rain as it is not to rain, the same odds as landing a heads when flipping a coin. The further below 50% we go, the further we move into less likely situations. As our previous probability of 35% snow suggested, it was not likely to snow, but couldn't be ruled out. And so although it might be more surprising that it has snowed, this highlights how the lower percentage chances can and do happen. In the same sense, you might have walked out one day when the weather report predicted an 80 or 90% chance of rain, only to find bright blue skies. This basic issue of both technological limitations, combined with the near infinite moving parts we have to consider when imagining future weather patterns, examples the limits of prediction, and how probability in this case acts as a guide between certainty and impossibility. And even with all this information, you can't be 100% certain about the weather. Where weather prediction might be considered taming the untamable, probability at a human level can help us to make educated decisions about the way we act. Although data varies from source to source, it's well argued that the probability of an airplane crash falls in a zone far above 1 in a few million. This compares pretty favourably to being struck by lightning, which is around 1 in 700,000, dropping to 1 in 3,000 over a lifetime. And vastly contrasts with car crash statistics, which skirt in the low hundreds depending on your sources. And where car companies recognise this, they too use probability to convince us that their vehicle is safer than the next. Here, a graph released by Tesla in 2018 pinpoints their Model 3 to have less than a 6% probability of injury, compared to, we have to assume, every other car company. Although here we see probability used as a tool to sell more cars, the idea of controlling and contextualising our risk perception can have long-term benefits for our mental health.
Now watch his technique. That's right. Brace the feet, address the handles, pull hard. Well, that's one way.
In the final part of this video, I want to concentrate on an idea called conditional probability. Typically, and confusingly explained in textbooks as, if A happens, what are the chances that B will happen? Which is not the same as, if B happens, what are the chances A happened? Similar they may be. We'll consider the stats first, and then fill in the blanks with some numbers. In this situation, let's consider what the chances are that someone has been infected by a virus, given they have had a positive test result. In our situation, the probability that a person has a particular virus is 0.8%. If a person has this virus, there is a 90% chance that, when tested, their result is positive. On the flip side, if someone doesn't have this virus, there is a 7% chance that they will have a positive test. If that sounds a touch confusing, let's now reverse back and fill in the blanks with some people. Our sample size in this situation can be 1,000 people. 0.8% of 1,000, the probability of having the virus, is just 8 people. 7 out of these 8 people will have a positive test result, and 1 will slip the net. Of the remaining 992 people who don't have the virus, 7% of these, so about 70 people, will have a positive test, or what's often referred to as a false positive. So in total, from our sample size of 1,000 people, 77 people will have a positive test, yet only 7 out of these 77 will actually have the virus. This means that only 9% of those who have tested positive have actually been infected. And this, in a nutshell, is how conditional probability works. What's often key within all these ideas is to make sure we're always asking the right questions at every step, rather than hammering away at the mathematics and excitement.
When you go through college, like studying physics and engineering, I studied physics. You have to answer the question that the professor gives you. You don't get to say this is the wrong question. In reality, we have far more degrees. When you're in reality, you have all the degrees of freedom of reality, and so the first thing you should say is this question is wrong. But like in the Hitchhiker's Guide to the Galaxy, the Earth is a giant computer,
Right.
And the Earth it comes up with the answer 42.
Yeah. Yep.
And to the question, like, so what's the answer to life, the universe, and everything? Answer is 42, and they're like, what the hell? That doesn't make any sense.
Right.
It's like, the hard part is the question.
The question.
The answer is the easy part. You need a much more powerful computer to tell you what the question is.
Right.